Start recording. And let's see if we can connect. Okay. Okay, good. Then unmute. I have to deafen myself. Okay, testing. Okay, demo mode. Okay, good. So hopefully you should be able to hear me now. Okay, so first of all, last class some students asked me about doing the assignment in the simulator. That would be too easy compared to doing it on the real robot, so I didn't want to allow that. However, if you're interested in the simulator, then you're in luck because on the 16th of December, there is the virtual Eurocup competition. Organized by the FIRA chapter for Moscow. So this is an international competition that runs the simulation league for Eurocup. It's the first time that we're running this. And so if you want to work with the simulator while doing the assignment or when doing the assignment, then you can do that if you have to join this competition then. Now, the challenge that you have to do in that case would be for the first assignment, you want to be able to do the sprint event at FIRA, which is 3 meters walking forward and 3 meters walking backwards. The simulation platform is Weebox. It's Weebox based, so there's some kind of setup environment that you have to use, but I'm not actually sure about how the I'm not sure exactly about the link that you have to install. But I'll get that later today, as soon as they respond to me. So if you're interested in simulation, then instead of balancing the ball, you can join the competition. There's no registration fee, which is nice. So the competition is on the 16th of December. On the 10th, you have to submit your software. Submit your program, and then they're going to run it on their computers. And then you can see. Now there's other events that we can do for the second assignment. Then which would be too late for the competition, but it would be okay for the assignment. And that would be, okay, here's the marathon. What do they do for marathon? can't watch YouTube anymore without getting annoying videos. Okay, so the marathon, I think your robot just has to run around in a circle. So the only thing interesting there would be how they measure the load on the battery. Because of course, otherwise, if you could run around like this, then if there's no battery that discharges, then the program, the simulation could just run forever. So that I think is a bit strange. So maybe we get them to do a better marathon. So the marathon is not so interesting, but if you want to continue with the simulator, then the second assignment, the project would be the penalty kick in soccer. That's not the one though. The soccer competition one would be here. Oh, it's uploaded. So which screen is that? That would be. So this will be the challenge for the second assignment. Then, if you want to do the simulator track. So you have a striker, a goalkeeper, and then 3 obstacles on the way. I guess that didn't work. Otherwise, they would have kept the video going. So, if you want to do that, then send me a message saying you want to do the simulator assignment. Until December 10th, then you have to complete the sprint. And until the December 28th, you will have to complete the penalty kick. Now, first one will be part of the official competition. The second one will be too late for the competition, most likely. So that will just be amongst this group here in the simulator then that we can run the game. Also, if you win first, second, or third at that particular competition, then you will get a scholarship and immediate admission to the Moscow Institute of Technology, which is the premier university in Russia, one of the top universities in Russia. You can go and study there right away if you win, I think, either first place or first, second, or third or something. So that's the opportunity that we can offer for simulation. So send me a message if you're interested in the simulation track for the assignment. Yeah. And that would be 2023. That would be December 25th. Okay, good. Then I shall. So last class we started talking about control theory, and we showed that even for a very simple physical system, like a ball that you're trying to hover between two gates, that in itself is a tricky problem, and the kind of intuitive approach with the bang-bang control is too simplistic. It will lead to unbounded oscillation. And in fact, lots of control problems have that feature that you need to worry about unbounded oscillation. Um, Now, what we haven't discussed is what can we do instead in order to actually make it work in practice, so that you can have a good controller for your system. In particular, for the first assignment, you need to balance the ball. So how can we develop a control for that? And what I'm going to discuss today is the PID controller, which I think is kind of like, for control theory, it's kind of like a Swiss Army knife. If you know the Swiss Army knife that MacGyver has, it has a knife and a saw and a screwdriver and all kinds of tools, and it's quite good at solving most problems, but of course it's not as good as a dedicated knife or a special purpose saw or a dedicated screwdriver. So with the PID controller, you can usually develop a reasonable control for your system with very little code and in reasonably short amount of time. And it's quite easy to understand as well. If, for many problems, if you want to have a better controller, if you want to do better than a PID controller, then usually you end up in a situation where, and I guess, yeah, control theory is a vast field, right, in engineering. Um, so there's been hundreds of years of research on it. But if you want to do something better than the PID controller, in lots of cases, you end up in a situation where you need to understand some advanced mathematics, which is not necessarily a problem. But in order to be able to do better, you need to have a more complex model. And that model then has a certain set of parameters. And given those parameters, then if you get the right parameters, you can do better than a PID control. But if you don't have those parameters, then your controller may actually work worse. So those parameters would be things like inertia matrices of the ball, the mass of the ball, the weight of the ball would be easy enough to measure. But the inertia matrices for a ball is also okay, as long as your ball is really just exactly round, like a wooden ball. But if it has some unevenness, then already that doesn't work anymore. And so for our projects, usually we start with a PID controller, and we get a controller that is sort of reasonably good. And then we look at ways to improve it if the control performance is actually one of the bottlenecks, or the PID controller may just work fine, and we don't need to improve on that aspect. One of the key lessons to learn from any kind of robotic system is that it is really an integration problem. Systems integration problem. What I mean by that is that, for example, you're trying to develop a robot that can compete in the FIRA competition, and you want it to walk for the sprint, you want to walk as quickly as possible. Now you develop a controller to track the path that you need to, or the marathon, you need to develop a controller to track the path, and you develop a very simple controller where your robot sort of follows the path in the marathon track, and then you say, well, but PID controller is very simple, we need to have something more complex, because that's what my professor told me, or something like that. Then what may happen is that you can spend a lot of time improving your path tracking controller, only to find out that the reason why you're not doing so well in the sprint is that your robot falls down too often, right? If that's your bottleneck, then improving the path tracking controller, if you cannot walk stably, is not going to improve the performance of your system. Similarly, you may develop a better controller that requires sensor reading, so it can detect exactly the distance to the path, but your vision system that you use in order to detect where the path is in the world, your vision system is not able to give you the accuracy that controller actually needs in order to perform better. So then you would have put in a lot of work into improving the controller, and then only afterwards realize that your bottleneck is not your walking gait or your path tracking controller, but your bottleneck is that your vision system simply does not see where it's supposed to walk. So any kind of robot system that you develop, you need to look at it as a complex system, and you need to find the weakest link in your system, the part that really is holding back your performance, and then start working on improving that. Just picking a part of the system randomly and then trying to make it better often doesn't lead to better overall performance because that part just happens not to be on the weakest link in your system if you just guess it. Often you have to do expensive tests and measurements just to find out where the weakness is in your system and how to improve it. So let's have a look at the problem that, actually let me do that slightly different. So So what we want to develop today is a controller for a slightly more complex problem. And the problem is kind of like a cruise control problem. For your car. And we can look at the scenario. You want to press a button. At the simplest case for cruise control, right? You want to press a button, and then you want the car to keep the velocity steady as it's moving along. So now, in order to maintain a steady velocity, what you need is a control, something that you can actually control. So that would be your gas pedal. Which controls the acceleration of your car. So the car is driving, there are certain forces that are acting on it. The engine is pushing it forward, wind resistance would tire friction would push it, would work against it, slow it down. So you have to continuously accelerate for the car to keep moving. It's not like in space, frictionless vacuum. So that's the first part. And then we want to have a couple of other features or things that make it more difficult. One would be that your road is not flat, but has ups and downs. Right? So sometimes you need to go up a hill, sometimes you go down a hill. So you need to be able to correct for that. And then you also need to worry about the driver doesn't always want to go at one particular speed, but wants to go at different speeds. So the driver controls a set point. To change the desired speed. So we want to come up with a simple mathematical simulation that allows us to model that particular environment and draw it. So think about that and see how you want to implement that yourself in Python or any other kind of programming language. So the first question that we need to think about is, if this is the car on a flat road, then we assume that our gas pedal can generate a acceleration that then combined with the mass allows us to calculate a driving force. And then there's some resistance force, which is the combination, the sum of all the forces that are slowing the car down. And we just assume that that force is constant. So then the question is, what happens when we go uphill or downhill? Hmm? Uphill it'll slow down, right? If you've driven a motor scooter or a car, then you will have noticed that effect. But how do we model this mathematically then? So here our car is on the flat, and it has some force pushing it forward. Now, when we are going uphill, I think what we can do is that now our forward force will be split into two components. One that is pushing uphill, and the other one perpendicular to this. So when we drive the vehicle now, or do I want to draw? Maybe I model it the other way. Actually, yes. We can do it this way. We have our driving force, and now that driving force is split into two parts. And if this part here is still pushing us forward, whereas this part here is the force that is required to push us uphill. And that one is sort of wasted. So that means that we're dealing. Okay, that would work nicely if we go uphill. But if we go downhill, we have the same picture. But our FD should be longer than so. So this would model nicely if I take the FD multiplied by the cosine of alpha here, then that would nicely slow the car down as we go uphill. But it wouldn't make the car go faster when we go downhill. So how can we? Yeah, okay. Um, yeah, I think we'll have to do it differently. So we have gravity. Gravity um, is acting on the car, and gravity is split according to this angle then. So here that applies gravity, which is then split into this component and this component. There it's pushing the car into the road. This part is the part that is acting against the motion of the vehicle or adds to the motion of the vehicle. So here we have G. And what's that component? So alpha would be here. Downhill. Then alpha. And this is 90 minus alpha. And this is alpha. And then this would be sine. Right, so when we go uphill, then our driving force is the driving force of the accelerator plus g multiplied by sine alpha. Um, and then, yeah, and then if it goes uphill, it must be g minus sine alpha. If it goes uphill, then the driving force is going to be reduced because for 0 degrees, then sine alpha is 0. So that term will not have any impact. Otherwise, if it goes uphill, then sine alpha is positive, and it will decrease our driving force. If we go downhill, then we get an extra speed boost because alpha is going to be negative, sine alpha is going to be negative, and then we will drive faster. So implement the Python model for this. You want to have an environment including the shape of the road, as well as you also want to be able to do different set points. Now, for simplicity, let's just say that we I mean, we could make the car drive in the simulation. Plot the position of the car. Okay. And then implement that. And just to make it look nice, we'll pick a position of the car. Now the car, I want to plot, since I want to plot the everything relative to the car, I think. So I plot the car at position x is equal to 0 and y is equal to 0. So the car is static, but the world around it will move. And I need axis to plot on. And I need, I may have to do some homogeneous transformations on it, so we can set that. So let's draw the body of the car. And let's take that to be the center of the, oh, I need an angle. So let's make the wheels 0.1. And circle has what? X, Y, and radius. So if the car is at 0, 0, then how wide should the car be? 4 maybe? 4, okay. So then that would be -2. Let's say -1.8. and the radius of the wheel 0.1, so that would be negative 0.1, and actually, no, okay, it must be this point. So we plotted at 0, 0, 0.1, and radius 0.1, and fill color, face color. Let's make them black wheels. And the back wheel 1.8, 0.1, 0.1, right? Oh, 3.6 meters. Then the position of the front wheel would be negative wheelbase divided by 2. And wheel radius 0.1. Actually, I can do all of this with just a single transformation matrix. So let's do this. And we need to calculate the homogeneous borders for this. And then this will be FC0. This will be FC1. This will be wheel radius. And then I can just not do any scaling, otherwise I end up in trouble. Circle, back circle. Okay, so let's see if we get something car-like. At least two wheels now. We would like to see them. Okay, and then here I need to set the limits. Negative 5 to 5. Okay, now here's my car. The wheels are a little bit too small, I think, for that wheelbase. So let's make it 5. Yeah, a bit too. Okay, so now we can draw the chassis. Oh, yes, and here is 3 dimensions. 0, 1, 0, 1. Okay, so then make the base of the car 2, the chassis height equal to 0.1, and then the cabin size would be 1, height is 0.2. So now we need to generate the cabin. So we start at 0, 0. And again, we need homogeneous coordinates. So, and then I need to go to, actually not 0, 0. It would be 0, 2 times the wheel radius. And we go to the positive, so cabin, no, chassis size divided by 2, 2 times wheel radius, 0, 1. Then we have the chassis size, then we go chassis size. Two times wheel radius plus chassis height. Then then we go to body size, cabin size divided by 2. 2 times wheel radius 1. Then cabin size, chassis height plus cabin height. And we go to negative here. And I think it's just this reverse. Negative. Then we go and close it to 0. I need these as column vectors, so we need to transpose them. We can apply a dot to it, and then polygon OSD closed equals true. Base color is equal to blue. Okay, now let's see if we have a car. Your input is shape 510. Come on, 510. Uh-oh. I have a blue thing, but not my car. So 0, 1, 1, 0, 0, 2, to 1, 0, 2, to 1, 0, 3, to 0, 3, 5, 0, 3, 0, 3, 5, 0, 5, negative 0, 3, 1, 0, 3, negative 1, 0, 2, 0, 1, 0, 2, 2. Yep. And that is just the following here. So points. This would be column vectors. So that means I want 0, 2 of this, and then I need to transpose it. And there's our car. A little bit too long. So the wheels are too small, so let's make the wheels bigger. 0.3. And the chassis. Okay, now we have the car, but now I want to make the wheels smaller. Right, so here's our car. can do things like rotate it, or I should be able to rotate it. Um, by 30 degrees. And I also move it somewhere else, so I need to rotate it first and then translate it. That works. Yeah. So now we have two cars at an angle. So we want to draw an environment. Or we want to set up an environment. So 10 meters. And we have 50 10 stops. From -2 to 2. Ten of those. And the first 10, I first 8 we leave at 0 so that we have a flat thing to start with. So that will be as easy as 20 here, 20 there, 25, 20 meters, and row 0, row 1, from 0 to 8 equal to 0.5, equal to, and 1, -8 is equal to 2 rows, 1 column, 2, 2 rows, 1, and let's just plot the environment. And that would be so now here we have a little mountainous region for our car that you can drive through. Maybe I need it instead of 20 meters, all this 1 kilometer. And our car. Okay, and then here we want to plot some, but actually, if I don't want to plot if I don't, if I just want to plot the environment, then I can only plot the angle. So that will make things easier. So that means here, 1000 multiply. And that would go from, let's do 10, so minus 4 to 4, 25 times 10 divided by 180 multiplied by multiply. So now instead of plotting the actual highway, I just plot the slope of the highway with derivative in it. And that shouldn't be minus 1, that should be 0. So here it goes up for a while, here it drops, here it's constant, up, down, different angle upwards. But this is now just the slope of the environment. So now when I plot the car, and I want to plot the thing at once. So I need to add x here. But that's not x where I want to plot it, but that's x in the environment. And then so now what we could do is, I need to figure out what the angle is at the environment at that point. So that would mean finding the nearest neighbor. So I could do a binary search. I wonder if there's a function to do that. Oh, there's search sorted. then I need to find the angle. The environment 0, and the value I want to insert is x environment, and that should return the index. So that returns 0. And let's average them out. So the angle will be environment. Does this return insertion points? So the environment 1I 0.5 times this I plus length environment 1 I plus 1 modulo length of the environment and 5 environment. This, this. So we need to rotate by Z, by the angle, by that to A, and so that we don't overwrite anything. So that should be AD dot A dash dot A dash dot A dash dot. Okay, now I also want to plot the environment. And that would be now I just want to plot this angle somehow to show it. So we'll go from -1 to yes, angle negative yes outside angle multiplied by 1 should be negative. I think tangent is sine, cosine over sine, right? Or sine over tangent is cosine over sine. Opposite over adjacent. Sine over cosine. And let's make it a road color. And extend them. We need to set our value. Okay, let's see what the graphic looks like. Mm, well, actually, let's see what we have here. So why does this look it? Oh, that is the problem. That's why. Um, so we need to also apply the transformation to this. So that will be -1. Yeah. It needs to be the column vector. Come this is on. Okay. This will only be A. Okay, now we have our car here. So we can try and make this a animation, and then see whether that works. We have no frames, then generate a frame. Zero, so that should be two. Frame dot extend harvests. Frames dot append frame. And then we want to do the simulation. So let's open animation. be correct. 1,000 seconds. So that's pretty neat. Now we show the car moving around on the road. So in order to control the car now, I simply want to have the current velocity. I need to pass in the current state of the car. I want to return the new car state. And for that, I need to pass in the current state and the desired speed that I want. And now let's just say if we accelerate the car, then we will get what speed. Um, so we set the current velocity and the current acceleration, and then what I can control is the acceleration. So my new velocity is going to be the velocity plus acceleration multiplied by dt, and I want the calculate a new output. Now the new output, I just set it to no output. And then I want to return a new state, which would be the new velocity. And so here we would have a very simple dummy controller just to test the system. So now for our PID control, what we have, what you can see there is we have a velocity that I want to reach. And now I can accelerate or decelerate the car, which means that I can control the integral of the velocity in a sense. The derivative of the acceleration is our velocity. So the controller that we want to implement is called the PID controller, which stands for proportional integral and derivative control. And it is actually fairly easy to implement, and also conceptually it makes sense. It's not too far off from what you would design if you were to have this kind of control problem. So now let's think you are the driver that is control. Can you check the Discord now? It's not connected to the So if you are driving and your target speed, you're driving on the motorway in Taiwan and you want to go 100 kilometers per hour, right? And at the moment you are going 80 kilometers per hour. So right now you're moving at that speed, then what would you do? And you're in a car, or in a motor scooter, so you can control the throttle. Now, if you're currently going 80, you want to go 100, then clearly you want to increase your throttle, right? Because you want to go faster. If you go 80 and your target speed is 100, then how much would you change the throttle? Because that's your acceleration, right? That's what you can actually control. Well, if you're currently going 80 and you want to reach 100, then if you are anywhere near a skilled driver, you would make a small change. Probably. Because you're almost going 80. You're almost going 100. So you want to add a little bit to the throttle. If you're going 20 and your target speed is 100, then what would you do? Then you would add a lot more to the throttle, right? Because there's a huge gap between 20 and 100, whereas the gap between 80 and 100 is much smaller. So you would add a lot to your throttle. Similarly, if you're going 150 and you want to come down to 100, then you would step off the accelerator quite a lot too. Maybe not as much as this, but in this case you would take off quite a bit of gas because you're going way too fast at that point. Okay? Whereas if you're going 105, then you would just ease off on the throttle a little bit. So this is actually the first part of your proportional controller, and that's what you would do naturally without having any mathematical sort of inclination. And you would say that what's important for the control is not necessarily the values that you have, but what's important for your control is your error. So we can define that your error at time t is the difference between, for the cruise control, the difference between your velocity at time t and the desired velocity, your target. at time t. And then your output of the controller would be based on this error. If you have a big error positive, you would add a lot. If you have a small error negative, so you're a little bit too high, you would set the control very small, right? Make a slight change to the control. Now the problem is you have these numbers. You have an error here, 5 kilometers per hour, let's say is your error. You want to change it, or you want to set a new control output based on that. In that case, it's not clear whether you should set it 5 degrees, decrease your accelerator by 5 degrees, or 5%, or 10%, or how much. That depends on the car. If you're driving a Toyota, then to go from 20 to 100 will require a lot of your engine power. If you drive a Ferrari, you don't really need to change that much. So we simply include that in our controller, but saying that there's some kind of constant that we need to choose that relates the error with the output of your plant, with the output of your car, for example, right? With the system that you're actually controlling, but that this particular relationship is assumed to be linear, which means we can make that value here simply a constant. And what will happen is if you design a controller, you can change that. As you increase your, and this constant is also called the proportional gain. As you change the controller, you can see sort of this kind of curve. If you start out with Kp being very small, 0, and then start increasing it, some positive number, you'll see that first you're going to approach your target speed very, very slowly, because your gain is very small. So even though there's 50-kilometer difference, you would only make a small change to the output is going to be rather small on your throttle. As you increase Kp, the curves are going to look like this. The slope, you're going to approach your target value faster and faster. And then, because here now the error is going to decrease, that means your control is also going to flatten out here a little bit. As you keep increasing your gain, you end up in a situation like that, where eventually you're going to start oscillating. Because you're going to go way too fast, then you're going to slow down, and way too fast, then slow down. And that would be the proportional part of our controller. Now, what should we actually do? Our optimal control may look like this. This may be the optimal control that we're trying to achieve. Something like that. We want to reach the target speed not in 60 seconds, but we want to achieve it in 5 seconds. And so we want to approach it fast enough, but we also don't want any oscillations around the target speed, or no large oscillations around the target speed. We only want small oscillations around the target. So the question then is, and actually for quite a few devices, this proportional controller is already doing a pretty good job. But the question is, if I'm here, currently I'm currently moving at this velocity here, should I now make a small change or a large change? Our proportional controller will say that we should do a small change, right? And we should have a small change to our velocity because our error is quite small. However, if I look at the trajectory, if my previous time was here and now I'm there, right? Then what do you think our change to the controller should be? So you want to go 100. Right now you're at 95, which seems pretty good. But a second ago, you were going 130. So in this case, it seems like if we don't do anything, if we use the same kind of controller, the next time step, we're going to be down here somewhere. So that doesn't, in this case, you don't want to add anything to the you don't want to, I should bring that point up here, then it's even better. In this case, you don't want to have a small change to the controller and reduce it some, but in fact, you would want to add quite a bit of throttle because you predict that the next time step you would have quite a large error and be much too slow. So now, what we're actually looking at is not just the proportional error, but we're also looking at the difference between errors. So this would be the error at time t minus 1. This would be the error at time t. So for our PID controller, we want to take our proportional part plus, and now I want to take the error at time t minus the error at times dt and divide it by some time constant. And I want to include that in my controller design. Now again, here, there's some relationship between how much we change our control output and how the physics of the world work and what the actual output is going to be. So there will be another gain, another constant here, kd, which we multiply by this value, and that would be our derivative gain. And that would be your D for the PID controller, because PID stands for proportional, integral, and derivative. And so we've now, here we have the proportional part, here we have the derivative part. If you look at the controller that is implemented in the servo motors that we use in our humanoid robot. Those are all running PD control loops. Another reason to use the derivative gain, or one thing why we want to use the derivative gain is, otherwise, if I'm approaching some target value, I usually oscillate and approach it this way if my proportional gain is high enough so that we approach it with the end. Using the derivative term, I can make it smoothly approach the target location, target velocity. Because here, the proportional part is still going to be negative, but as I approach, the amount of the error is going to reduce, which will mean that there will be a negative term on the KD that we multiply. So as we get closer and closer to our target value, we're going to reduce our controller output. So now that's already the P and the D part. Now we just need to add our integral term. Now the integral term relates to the fact that sometimes it usually occurs when your controller is discretized. So you can send it to your throttle to 10 degrees or 15 degrees, but not to 12.7 degrees. Right? Now, if you want to drive 60 kilometers per hour, this is your target speed, and your control is somewhat, either it's non-linear or it is discretized, then it may not be possible to find the exact throttle setting at which your car will go 60 kilometers per hour, which means that you'll be slightly below, maybe 58, and then this is setting 3, and if you change it to setting 4, you will be slightly too fast, 61 and 59 here. So in order to, in this case, we cannot get the current speed to be exactly 60, but what we would like to do is at least average it out over 10 kilometers. So we go a little bit below, and then we go a little bit above, and then we go a little bit below. So in order to do that, we calculate the sum of our errors. Because for this component, I need the integral of our errors. And this is called the integral term, or integral gain, because we also apply a constant here. So we have 3 constants, Kp, Kd, and Ki. But that's it. That's our proportional integral derivative controller, our PID controller. So the implementation of it in a discretized system is not difficult. All you need to do is calculate the error between your current performance and your target value. The difference between those, that will be your error. And then you need to calculate the changes in the error. And then it depends on your that depends on your um, here it depends on if your system is really synchronized. So if you have a hard real-time system, you will get a reading every you get a reading 50 times per second. Or if it's a non-hard real-time system, in which case you get readings approximately 50 times per second, but there will be some latency and some jitter between the readings. So in this case, you need to actually keep track of the amount of time that has elapsed between, yeah, no, that should be divided. The amount of time that has elapsed between the current error and the previous time's error. And then here we have our integral term for the summation error. Now, when you're implementing your PID controller, then this part here is all very standard. Calculate the error, calculate the difference of the errors, and divide it by the time difference between the two samples. Sum up the time samples and multiply them with the time that you actually have. That part is very straightforward. So now in order to actually implement the controller, you need to only, the tricky part is to find these three constants. Right? The rest of the code is always exactly the same. The only thing that you need to do is you need to find those three constants, and that's what's called tuning your controller. Now, to tune your controller, that basically means finding Kp, Kd, and Ki. And there are various tuning algorithms for the PID controller. One of the most popular methods for tuning your controller is the Ziegler-Nichols method. And that one is as follows. You set your gains all to 0. So initially all your gains are 0. Then the first thing you tune is your proportional gain, at which point you keep increasing it until your system starts to oscillate. So you keep increasing until you oscillate. And then you divide it by 2 or 3, your current gain. So you keep increasing your proportional gain. At 15, your system starts to oscillate. Then you reduce it, set it to some value between 5 and 7.5. Then you tune your derivative gain by having a controller and you change the set point. So you have your controller, you control, and then you change the set point by 5 to 10%. And then you increase KD until, so now there's a change, right? Your target value is here. After a time you want it to be there. Your controller is operating like this maybe. And then without the KP, there's going to be a sag. It's going to, without the KD term, there's going to be a sag. It's going to drop further, and then it's going to control at the new set value. You increase that until you don't get a large overlap there. So once your controller does this, then that will be the correct derivative term. And then lastly, you tune your integral term, integral gain, by increasing it to reduce any kind of steady state error. So steady state error would be your set point is 100, but your car keeps driving at 92 kilometers per hour, 95 kilometers per hour. Then you can increase your integral term in order to get rid of it. And it's going to, if it's too low for too long, then it's going to accelerate it a little bit more. And that's it. That's the Ziegler-Nichols method for tuning the PID controller, which works surprisingly well in practice for many different kinds of control problems. Now, one thing to keep in mind is this integral term here can be tricky. Because you may have what's called integral windup. And that was kind of interesting to see in the early days of the soccer playing robots, because you could tell which teams had only just gotten their first robots and which teams had been using them for a little bit longer. In case in point, there are actually chips you can buy that implement a PID controller, which at, at that time, 1990, the microcontrollers were not nearly as powerful as nowadays. Nowadays, you can have a Jetson Nano with a GPU built in, and it can control your robot. But at that time, they weren't so powerful. So they weren't powerful enough to run the PID control loop at high enough frequency to control your robot well. So a lot of teams implemented hardware supported PID controllers. So they used extra coprocessors, extra chips to do the PID control loop. And then you could tune them, and then they would generate the desired current on your motor so that the robot would be able to drive at a given speed and also rotate at a given speed. Now, the integral terms were also implemented and tuned by lots of teams when they first got the chips, because the chips already had them implemented. But the problem was that when your robot was driving, and because of the error in the vision system or because of other robots, your robots may have been driving here and now trying to move forward. But now there's another robot from the opponent team that wants to drive this way. Or the robot wants not to drive forward, but it wants to turn to the right. Say it wants to turn to the right. In this case, the left wheel would show a large error, and it will be trying to turn, but because there's the other robot here blocking it, the system would simply not turn, which means that if you think of it as the PID controller, that means that this sum here now would grow very large because you want to rotate, you want to go 1 meter per second, but you're constantly 0 meters per second. So the robot would sit still, that would take 10 seconds. It would add up a lot in the integral term. And now this robot drives away. So once this robot drives away, your PID controller is going to add more and more power to the left wheel because it wants to turn, but it can't because it's blocked. Now when that blockage is gone, you're going to have a robot that spins incredibly fast on the spot. And you saw that in the robot competitions very often with teams that had implemented the integral part of the controller and added some gain. So you would have robots, they would be blocked, then one robot would drive away. You would think everything is fine for this robot, but now because of the integral wind up, the output would be very, very fast. So it would be going maximum speed to the right. So it would spin like crazy, which then had the problem that the vision system wasn't fast enough to recognize a very fast spinning robot, which means that the robot wouldn't even be able to get feedback from the vision system telling it that it's going much too fast. So then this was a lot of fun. Then people had to try and catch this robot. Or, of course, if it's going forward, then it'll just shoot into the wall very quickly at very high speed. It'll go off like a rocket. And the reason for that is what's called the integral windup. If you're trying to control but something is blocking your control, then this term can sort of grow arbitrarily large, which is a problem. So the solutions for that is if you do have a non-zero integral gain, then usually you need to implement at least the maximum that you want to allow for the integral for this sum. You want to make sure that this sum is capped at least, so it doesn't grow to infinity, or you can do a window integral system where you say, okay, I only sum up the error over the last 5 seconds or over the last 5 minutes or whatever it is reasonable for your domain. And this is the the error that you're willing to include in your integral calculation, but the other parts you want to exclude, you want to ignore. Another way would be if that this could occur would be if you change the set point drastically. So if your set point is here, and then you drop it down to here, and your controller has been going for a very long time here, now you're changing to there, then what you want is this, right? You want it to approach your new set value very quickly, but what may happen is that you'll actually go like that. Because all of this error here, if you sum it up, this may be a very large error that has accumulated. Right? In fact, if this goes back to when you started your robot, when you started your car, and when you drove out of the parking lot, you were 2 kilometers too slow, right? That may have an impact an hour later when you're on the motorway, if you simply keep adding up your integral errors. So that's why the integral term requires a bit more thought. But actually lots of control problems, you can come up with a good solution by having just the proportional and the derivative component. So ki, the gain for the integral term is either very small or 0 lots of times. If you don't set it to 0, then you do need to worry about integral windup, and then you need to implement either a max clipping function, maximum or minimum. I mean, because the sum, the error here could grow positive to infinity or negative to infinity. Right? If you are constantly below, or here you could also be constantly above, which gives you a very large integral on the negative value for the. And that's the implementation for the PID controller, or the theory of it. We started the implementation with the car, you know, the simulation of the car. So I suggest until next class, you can implement a PID control using this control function here, extend it to tune the car and the controller for the cruise control, and also then you can add things like the environment. Like what it plots right now, it will show the angle of the road. Then you need to change how much the car will accelerate given a particular control output based on the slope of the road. Then that'll make it a bit more interesting. So try and implement your own control function here, and then tune it for the car here. The rest of the implementation, calculating the error, calculating the difference between the errors, and calculating the sum of the errors is always the same. So once you implemented one of these PID controllers, you can use it in many different applications. The only difference would be the constants that you use, the gains that you use, proportional gains. So really, in order to implement a PID controller, all you need is 3 numbers, 3 floating point numbers. And then you can use the same thing for the assignment, because in the assignment, your target is to balance the ball on the rail. So then you have the ball, you have a target location, this will give you your error. And then you can control the slope, that will be the output of your controller. Okay, good. Then that's it for today. Again, if you want to do the simulation assignment, then you have to send me a message. Otherwise, you have to do the assignment on the rear robot. Using the rear robot, you need to balance the ball and also do the 2D marble. But the 2D marble maze is much easier than the balancing of the ball on the rail. Okay, good. Got